Hi, I'm Timo Stamberg, and within the next 30 minutes I would like to show you what the research of my doctoral thesis has been about. And I want to start this presentation with a definition of land cover mapping. Land cover mapping is the identification of physical and biological materials on our Earth's surface. This can be, for example, forest, water, wetlands, or barren land. And it plays a significant role in several applications. Examples are environmental monitoring, crop type mapping in agriculture, resource management, or change detection. And typically, land cover mapping is realized using remote sensing data. So for example, a satellite image, as you can see here. Specifically, this has been a multispectral satellite image from Sentinel-2. These satellites detect the sunlight that is reflected by the Earth's surface. And they do that in the visible, but also in the infrared spectrum, which makes them ideal for monitoring vegetation. And the data from Sentinel-2 is open access, so it is free to use. But how can we analyze all this huge amount of data? We can use machine learning, because it has been successfully used for land cover classification, as it is well suited for extracting complex patterns from data. And it enables an automatic and large-scale mapping. However, there's one downside of using machine learning models, and that is that the decision-making processes are often not transparent. And this is a problem because land cover classification supports social, economic, and political decisions, and therefore understanding the predictions is essential for trust and for responsible use. Therefore, in my thesis, I have done research regarding the explanations of convolutional neural networks, and I have improved these explanations by proposing a specific architecture that is interpretable by design and proposing an attribution harmonization method that improves the explanations of existing methods. In this talk, I'm not going deeper into feature-specific attribution methods, which I have also proposed. And then in the second part of my talk, I am going into naturalness mapping. So how I have used the methods from the first part to present a novel approach for naturalness mapping and large-scale mapping. And here in this talk, I am skipping the part of my thesis about change detection. So let's start with the first topic, improving explanations of convolutional neural networks. And here I want to start with a more formal definition of multi-label land cover classification. In this satellite image, you see several land cover classes, such as water, grassland, built-up, cropland, and forest. And you can put these land cover classes into a list, which does not only contain the land cover classes present in this image, but also those present in the whole dataset. And as a formal representation, there's a target vector with ones indicating that the class is present in the image and 0 indicating that it is not. Deep learning models approximate a mapping from the input to such target vectors. And this is realized by optimizing parameters using training data. A specific type of deep learning models are convolutional neural networks. They are well suited for analyzing images. And they are structured by having several layers. Each layer performs a filter operation, resulting in a feature map. And you can imagine a feature map being something like an image with a high number of channels. When we have trained such a neural network, it can do predictions. Here in this example with numbers close to 1 indicating that the class is present in the image and numbers close to 0 that they are not. But the question is now, where is the model actually looking at to make these predictions? So let's, as an example, have a look at the build-up class. There exist attribution methods, and one of these methods is gradients times features by Shrikuma et al. Here you compute the partial derivative of the output with respect to the features, and then you multiply that with the features and you sum that over the channels. And if we do that for the build-up class, you get an attribution map, as you can see here, with red indicating positive contributions and blue indicating negative contributions. And as you can see, this explanation is really noisy and it is hard to interpret for human. So as a next step, let's compute attribution maps for every land cover class. What we get are 8 attribution maps because we have 8 classes, and because this is a lot to visualize, we reduce this visualization by showing only the class with the maximum attribution value. And as you can see, it's still noisy, it's still not really interpretable. But if you think of it, the pixels in the input image, they represent only the spectral signature without any neighborhood information. So these pixels contain only low-level information. But this differs if you go to deeper layers. Here you have deep feature vectors and they have neighborhood information and therefore they represent high-level concepts. And if we compute attribution maps at deep layers, they become much more interpretable because the features are more high-level. And as you see here in this image, the build-up class, for example, indicated by gray, is mostly presented in the middle of the image. And this aligns quite well with the actual location of the build-up class in the satellite image. However, calculating attribution maps at deeper layers has one downside, and that is that deeper layers usually have a lower resolution. What we propose is an architecture, the UHNet, that gives you high-level explanations at high resolution by providing a deep layer in high resolution. And here you can see the architecture in more detail. So it consists of a UNet by Ronneberger et al. And this UNet has skip connections that establishes a strong link between the input and the deep features, resulting in an interpretable feature map. And then the head of our network architecture performs the classification using this high-level feature maps. And as you can see, the explanations of this specific layer of interest, they are high-level, interpretable, and high resolution. And we have published this idea of this architecture in 2021. The UHNet architecture comes with a limitation, and that is that it may come at the cost of reduced classification accuracy under certain circumstances. And with that, I would like to continue with the second part of this talk, attribution harmonization. So before I have shown you one attribution method called gradients times features. However, there exists a bunch of different attribution methods. For example, Grad-CAM, where gradients are averaged across channels to reduce noise. There's integrated gradients, where you compute gradients along a path from a baseline to the feature map. There's layerized relevance propagation and deep lift, which do not exactly compute gradients, but have another strategy of backpropagation process. And there's gradient shap and deep lift shap, which are very similar to integrated gradients and deep lift, however, use a baseline that is determined by the training data. But there are not only gradient-based approaches, there are also perturbation-based approaches. As an example, there's occlusion sensitivity, where you occlude parts of the feature map and measure how sensitive the model reacts to these perturbations. And there are much more. And if you compute these attribution maps, you can see that the results can look very different. To give you some examples, if you compare gradients times features with Grad-CAM, you can see that gradients times features is much more noisy. If you compare it with sliding window occlusions, you see that the resolution is lower because you have the patches with which you have occluded the feature map. And if you compare it with integrated gradients, at the first look it might look similar, both are noisy, but if you look more closely you can see significant differences. So therefore, the research focus within the last years has shifted from how to compute attribution maps to which attribution maps should we actually use. On this challenge, we provide a completely new perspective. We consider that an attribution method is an approximation, and we estimate the attributions of feature vectors in general. And in the next slides, I want to show you how we do that. After that, I'm going to show you our results. So I want to introduce the feature space, showing you a very simple example. So imagine we have the whole training data, and for simplicity, we consider that the channels are only red, green, and blue. So we have three-dimensional feature vectors here. The pixels are three-dimensional, and therefore the feature space has also three dimensions. One axis corresponds to one channel. But what is so special about this feature space? It's special because here similar pixels are close. As you can see, these brownish occurring pixels, they can occur very far within an image or even within different images, but in the feature space they come close together. So here similar colors are close. And if we bring that idea to a deeper layer, of course we have a feature space with a high number of dimensions, but the statements here are quite similar. We would say within an entangled deep feature space, not similar pixels, but similar high-level feature vectors are close, and high-level feature vectors don't have colors, but they represent concepts which are close. And when concepts regarding the predicted classes are close, then attributions should be close as well. So let's have a look how this feature space looks like if we reduce the dimensions and if we compute the attributions using one attribution method. And as you can see here, there seem to emerge some clusters, with this example cluster having attributions that are mostly aligned to the build-up class. So now that we have analyzed the feature vectors using the training data, we can look up the attributions for test data. And I'm going to show you how that works. So in the first step, we compute the feature map of this input image. And then for each feature vector, we have a look where is it located in the training feature space. We then do a k-nearest neighbors regression to compute the attributions, and then we know the attributions of this feature vector and can align it with the input image. And as we do so, we get more consistent and also better explanations. So if you compare the original attribution of gradients times features on the left-hand side and on the right-hand side, you can see that the harmonized attributions align much more with the actual location of the land cover classes. So for example, the build-up class, these 2 or 3 water bodies, the location of the forest. But also, you can compute these harmonized attributions for any attribution method. And if you do that for integrated gradients, you can see that the harmonized attributions are much more consistent compared to gradients times features. And also for sliding window occlusions, we even increase this low resolution due to the patch size. And so all of the harmonized attributions are much more consistent. And this shows you only one sample image, but of course we have computed Pearson correlations for the whole test data sets. So what you see in this matrix here are the pairwise Pearson correlations between all methods. And I don't want to go deep into all these numbers, I just want to show you that for the harmonized attributions, the Pearson correlations are much higher. We have repeated these experiments using 3 different CNN architectures, using 3 different data sets, 10 attribution methods, and each experiment has been repeated 10 times using different weight initializations. And the outcomes all lead to the same conclusion. So to conclude on attribution harmonization, it yields more comprehensive and more consistent explanations. It also makes the choice of attribution method less critical, and it works for any attribution method and any CNN architecture. And we have published this idea in 2025. There is one limitation of attribution harmonization, and that is that it is constrained by the degree of entanglement within the learned feature space. Therefore, it is only applicable to deeper layers, but for shallow layers, the outputs would be misleading. As a future direction, it would be really interesting to see if this would also be applicable to vision transformers. However, there's an ongoing debate regarding the interpretability of attention mechanisms. And therefore, in our initial experiments, we did not get any successful results. However, I assume that if you use some tricks, you can probably transfer this method also to vision transformers. And with that, I would like to continue to the second big part of my thesis, and that is mapping naturalness. But why is naturalness actually important? Well, natural ecosystems like the Sarek National Park in Lapland, that you can see here in this satellite image, offer important benefits. For example, they play a key role in preserving biodiversity. They filter air and they purify water. They absorb carbon dioxide and thus regulate climate. And they supply pollinators that are also important for crops. And therefore, mapping naturalness would be a valuable tool, because you could track human pressure on naturalness, or you could track conservation efforts. You could inform policy making and support land use planning. There exist already some traditional naturalness mapping approaches. Examples are the human footprint by Sanderson et al. Or the Human Modification Index by Kennedy et al. These traditional naturalness mapping approaches are based on indicators such as population density, agriculture, transportation, or electrical infrastructure. And to show you how this looks like, let's compute the human modification for the Sarek National Park. So these traditional approaches do not account for vegetation health, for example, and they result in a low spatial and a low temporal resolution. And therefore, we propose a novel approach using machine learning, which enables us to find natural patterns in Sentinel-2 imagery. And as a result, with our approach, we can account for environmental effects of human activity, and we get maps in high resolution. And there's one challenge, and that is accurate labeling. So how could we actually label naturalness? So here we propose a novel approach for naturalness mapping. And in the first step, we create a data set of protected and anthropogenic regions. So as you see here, we focus on Fennoscandia, that are the countries Norway, Sweden and Finland. And we are looking for protected regions and for regions with high human pressure. We call that anthropogenic regions. In the next step, we then export Sentinel-2 data from these locations, and we label them with 0 and 1. And this data set is already novel of its kind, and we have made it available open source. In the next step, we train our novel UHNet architecture I've shown you in the beginning on this image-wise classification task. And when the model has been trained, we find the spatial patterns associated with naturalness by computing attributions. And here I'm showing you how original attributions look like, so not harmonized attributions. And as you can see, they look very inconsistent. And this is because we have to divide a large-scale image into smaller patches with the same size as the training data. And thus, the original attributions become inconsistent. However, if we compute harmonized attributions, we can compute the feature maps and then come to the harmonized attributions. And this can be done for large-scale mapping because you get this spatial consistency. And this is a capability that was previously unavailable. So now that we can do large-scale mapping, we can do predictions for all of Fennoscandia. And we do that. So when we are looking for where natural and anthropogenic regions are located, we can see that in the northern regions and along the Scandinavian mountains, there are predominantly natural areas. And in the more southern regions and the coastal regions, we have anthropogenic impact. When we set a certain threshold, we predict that 44% of the Fennoscandian landscape is natural. And this aligns quite well with the human modification by Kennedy et al., which categorizes 42% of having low human modification. We can also do further analysis by comparing our naturalness score on the y-axis with the traditional human modification index on the x-axis. And we can see that those values have a correlation. So we compute a Spearman rank correlation of 0.75. 1 would be the highest, 0 would be the lowest possible value. And we can see that for low to moderate human modification, we have kind of a linear correlation. And this already covers 91% of the Fennoscandian landscape. And you might wonder, on the left-hand side of this plot, oh, what is here happening? There's an anti-correlation. And yeah, true. So this aligns to the city centers mostly, which covers only 0.2% of the Fennoscandian landscape. But yes, here our model seems to do something strange. So to conclude on the naturalness mapping approach, I have presented you a novel satellite and machine learning based methodology to perform plausible and large-scale naturalness mapping in high resolution. And we have published this idea in 2023. You might have wondered, this sounds a bit like weakly supervised learning. So we start with image-wise labels and we end with pixel-wise predictions. And yes, true, that's a huge similarity. But there's also a difference compared to weakly supervised learning, and that is that we do not predict classes, but we uncover the learned patterns of the model on a continuous scale. However, this distinction between our approach and weakly supervised learning is not clearly defined. There are also some limitations of our approach. So, for example, the comparability of scenes is limited due to fluctuations in the satellite imagery. Such fluctuations can be climatic variability, changing snow cover, clouds, or topographic shading of mountains. And as an outlook, it would be really interesting to implement this in a global way, not just focusing on Fennoscandia. However, here we have a challenge that in many biogeographic regions, let's say for example Germany, we don't have true natural areas, and therefore we are lacking in training data for such regions. I've already included some smaller conclusions along the way, and now at the end of my presentation I will give you an overall conclusion about our overarching contributions. So by improving the explanations of convolutional neural networks, we contribute to more interpretable and more understandable explanations. And this supports more trust in model predictions. We therefore promote to reliable and transparent applications of machine learning in remote sensing and environmental science. And on the mapping naturalness side, we contribute to a large-scale mapping based on attributions, which is only possible due to our novel methodology, attribution harmonization. And with this, we enable satellite-based naturalness mapping. I have also contributed as a co-author to some other projects. And with that, I would like to thank you for your interest and for watching this video.